Hello and welcome to our webinar, where we explore a case study on reverse engineering a decommissioned swing bridge using the power of 3D scanning and Geomagic Design X from Opton. Learn how Or3D, a leading 3D measurement specialist, successfully overcame a real-world engineering challenge by creating a digital twin of a twisted bridge, restoring it to full working order using advanced simulation techniques. If you're in the fields of civil engineering, infrastructure management, or 3D modelling, this webinar will show you the step-by-step methodology used to reverse engineer large-scale structures and ensure functionality through virtual testing. Learn how digital solutions can replace risky and expensive physical testing by leveraging precise digital simulations. For those of you who are not familiar with Or3D, Or3D is a leading 3D measurement and reverse engineering specialist based in the UK. We provide innovative solutions for complex engineering challenges using advanced 3D technology and CAD modelling software. So, I'm going to introduce you now to Sean Keane and Robert Wells, our engineers and the brains behind this project. So, let's start by introducing what the situation here. A swing bridge was hit and left in an open position after a collision. And Or3D's goal was to restore its functionality. So let's talk about the issue here and what you were addressed with, how Or3D, the initial thoughts on how we were going to do this, and the planning side of things.
So, yeah, a little background, I guess. The client approached us with the problem that they have a swing bridge, which is currently out of action because it's been hit by a vessel running through their dock.
Yeah, a couple of times, I think.
Yeah, it's certainly very twisted. And the problem they have is they need to get this swing bridge recommissioned, but they were very worried that if they tried to swing the bridge, that it would clash with some dock furniture and therefore
get stuck.
And get very stuck, and then therefore close the dock off to water traffic, which is going to be a big no-no. So, having worked with us a few times before on some fairly high precision projects, they asked if there was anything we could do to maybe simulate the motion of this bridge and see if it was going to get stuck, and if so, where would it get stuck, so they could take account for that before they
mitigate it.
Yeah, exactly. So, fortunately, we'd been to site a few times before and we had a pretty good idea of the location of the bridge and the kind of challenges it would involve. So I think the main ones for us were...
And we'd actually done some work on a very similar bridge at the same site previously.
Yeah, exactly. That one didn't have the same problems, but it was the same kind of mechanism in that it sits on a
It's still
pintle.
the same swing bridge arrangement, isn't it?
Yeah.
Where it swings out, connects the two sides and allows traffic to flow.
Exactly.
But this one was a little bit more damaged.
Yeah. So I guess to explain to everyone, the bridge sits on a central pintle, which constrain 3 degrees of freedom, and then there are some rollers and a roller track which run on the tail of the bridge, I guess. And so...
I suppose we should be more specific about those degrees of freedom. All rotations, basically. Because it allows it to pivot up and down, and side to side, and rotationally around as well.
Sure.
Because the bridge actually moves up and down on some blocks, which allows it to rise high and come over. Obviously I'm exaggerating the movement, and then at the final resting plates then lower itself onto the bridge.
Yeah.
So it is moving in all rotations.
So we needed to really understand that central pivot point.
Yep.
And we needed to understand how the bridge would then move from that point. So I guess the first challenge for us was understanding how we were going to capture the data. Okay, so at Or3D we've got a range of equipment, everything from sort of industrial CT all the way through to drones for bigger scale projects. But this was quite an interesting project in that it involved very precise data, but also over quite a long range. So that led us down probably the terrestrial scanner route, of which there are a number of options. Eventually we chose the Trimble X12 for this project, primarily due to the fact that it has a very long range. Of course, what we haven't explained is that realistically we only had access to the dock from the bridge side, and we needed to capture the furniture over here.
Yeah.
So we needed that long range data, but it also had to be really, really clean.
Yeah, roughly the bridge is about 70 metres long.
Yeah.
This is the site that a kind of rudimentary version of the site that we captured. So yeah, it's about 70 metres by 70 metres, roughly.
Yeah, absolutely. But also on top of that, we have the issue that you might be able to see that the bridge sits very, very close and low to the dock, which gets covered in water. The tide comes in and it completely floods all of this area. Yeah, there's a bund wall around here to keep the tide out, but all of that gets completely covered.
Nice.
Yeah, so, and in fact, all of this had standing water in, so the client had to add some sumps in there to pump all the water out prior to scanning. And it was grim. It was just full of mud and all kinds of nasty stuff. Crabs walking around in there and all sorts. Yeah.
I was fortunate enough not to be on site for this job. I was just driving the computer on this one.
Yeah. But also it meant that we had to put the scanner in some locations which were really close to the dock, and we needed to make sure the system we used captured very clean data and it didn't become
you can deal with that short standoff like a lot of terrestrial scanners.
Yeah, certainly in days gone by they struggled with that short standoff.
Yeah.
So the Trimble X12 sort of answered all those questions for us.
Certainly did. Good bit of kit.
All things aside, there was a very dirty tripod and engineers on site at the end of it, but we got there and we got all the data required on site. And again, with the X12, what's really nice, we have the tablet with the system, so it does all the on-site registration.
Really
we
nice.
can see the data in 3D as we're scanning, give us and the client a warm fuzzy feeling that we've been able to capture everything, and make sure we've got no dead spots in the data. There's some particular areas on this site where in some cases we can interpolate the data that we reverse engineer, but generally there were some areas which we had to have every square centimetre sort of accounted for. Yeah,
specifically around these concrete areas where we knew there was potential for collision.
Yeah, and the roller track, of course, which is going to have a big effect on the motion of the bridge.
Yeah, because the area of pivot is, the point of pivot is so far back. Obviously, any deviation on the rail that it runs on rollers, is going to have a massive effect on what the end point is doing.
Yeah. So once all the scans have been collected, I think there were probably 100 or so scans for this particular project. We took that back to the office, pretty much gave it to you, but we put it through RealWorks, that's the Trimble software.
Finish off the alignment, just make sure that everything is perfectly aligned before we start reverse engineering.
Yeah. So data's exported from RealWorks into Design X.
Yep.
What's the next stage, Sean?
Well, first of all, we need to get it into some sort of sensible coordinate system for modelling. Whenever we model, you start out from zero and you build out. Anybody that's done mechanical modelling will know all about this. Is that you need a known point from which you can build out on. When you reverse engineering, it goes the other way. You've got a known point, and you need to bring your scan data aligned with that so that you can build in a sensible way square to your coordinate.
We need to move the scan data, which could be in an arbitrary location, back to a design coordinate system.
Correct. Yeah. So for us, the obvious one was to centre everything around the pintle, the centre point of the pintle, which had its own problems because although we've scanned all the data, the actual pintle itself is concealed. So we managed to get our hands on some old drawings of the bridge and infer where the pintle was. I think we used the body in which the pintle's
it's like a big cylindrical block, isn't it?
Yeah. So
and
we
massive
had a flange. And then we had a big flange that we could offset from to infer the actual pintle position.
Yeah.
And we based our entire coordinate system on that pintle position, and then aligned it in with the.
I think we used gravity, and then just made the bridge square as the bridge could be.
We made the bridge square in its current position now, because that's where it had been left. Obviously, not covering the waterway, and then we're ready for modelling at that point.
Excellent.
Yeah.
So the data's inside of Design X. We've aligned it to the coordinate system. We've used some of the amazing point cloud processing tools inside of Design X to give the data a nice even point spacing,
Yeah.
keep high resolution data in the areas we need it, like the pin tool and the roller track.
And it's worth mentioning that we did actually mesh this data. There's a few benefits to mesh.
Yeah.
So instead of it being individual discrete points, we've then triangulated those points, which gives us a nice mesh. It's just a bit nicer to work with.
Yeah.
And it has a few advantages.
Sure.
And we felt for this job that would be nicer to work with.
So then we kind of modelled it in a couple of different ways. There's a big aspect of this is going to have to go into a simulation package. So we need to model it in a parametric kind of way so we can create the mates and the constraints between the bridge and the dock so that we can simulate that movement.
Yep.
So I think the majority of that was done parametrically.
Yes.
So we made a perfect sphere, for example, found a perfect centre point and that kind of thing.
Certainly for the pintle, yes.
But then for the roller track, we needed to know all the undulation of that roller track.
Yeah, because we wanted to know what the contact point of the rollers on the bridge and that track is obviously going to make the bridge do this. Yeah. And we needed to capture all of those.
Yeah. There was also some concern actually, was the roller track concentric with the pintle? And in fact we found that as the bridge was probably going to rotate, we're jumping ahead a little bit, but as the bridge was going to rotate around, it looked like that it was going to get quite close to actually falling off the roller track as well.
It didn't, but it was close.
Yeah.
It wasn't concentric, but there was sufficient depth in the rollers themselves to compensate for that, although increased wear obviously. And the other place was specifically on this corner where there was quite a lot of damage. We needed to have a very faithful representation of the concrete.
Yeah, we couldn't just assume it was nice and square and perfect. It wasn't had rebar sticking out of it.
Basically, anywhere where there was definitely going to be a near contact point, we needed to model with the utmost accuracy. Yeah. Because it again, jumping ahead, but it did come down to millimetres. So we needed to ensure that we were modelling to well below millimetre accuracy.
Absolutely. And so I guess in those areas of high curvature, it's worth mentioning that we use some of the exact surfacing tools in Design X to create a very organic but true to life representation.
Yeah. So we've got quite a few tools. Mesh Fit being the obvious one. Really powerful tool to quickly extract surfaces off from mesh into a NURB surface, well, into a CAD surface.
Yes.
And that is one of the benefits of having mesh.
Yeah, absolutely.
Is the ability to do that, because it is as simple as selecting the data you want, tweaking a few settings. Sure, you've got the control should you need it. You can also just click yes, but there's some control in there to actually how tightly are you fitting in.
So we've got all of the data imported. We've aligned it to the design coordinate system.
Yep.
Now we need to go through the modelling process. And I guess there's two different ways that we can attack that modelling, or three maybe. So we've got parametric, design intent. Yep. We've also got parametric as is,
correct,
and then true, fully organic as is condition. So we used all three.
We used all three. We used parametric when we were trying to infer the position of the pintle I spoke about before. So doing, nominal offsets and, constructing geometry relative to each other. As is, parametric was how we modelled most of the bridge.
Most of the steelwork, most of the
steel
I-beams, that kind of thing. Because I remember looking along the length of the bridge and looking at one of the pieces of steels, and it was going all over the place, twisting and all kinds of things.
So instead of the I-beam being a simple extrude, we instead made it a sweep with a twist along.
Yeah, so for example, the thickness of the beam is pretty constant. But the position of it is definitely varying from an ideal extrude.
So that we can capture the flex and the twist that's happening in real life. And then the third is the organic modelling, which is still a CAD surface, but it allows us to follow the underlying mesh very, very faithfully. And one of the main tools that we use for that is Mesh Fit. That's one of the reasons why we spoke about before that we did actually mesh it before we started modelling. And one of the reasons is that we can then use the Mesh Fit tool And what that does is it looks at your mesh selection. So you select an area of data, and then you say, I want to create a surface on that, and then it fits the surface to that data. There's a few parameters you can tweak, so you can get it how tightly it fits it, or you can smooth it out, because sometimes that's really preferable. You know, if like, for example, completely different case, but if you're doing a casting, you can smooth the surfaces out. But in this case, we wanted it to really follow it, so we made sure those parameters were quite tight, so it did follow them. Because in the areas of concrete where we had some really damaged areas of concrete, but they were also areas where the bridge was highly likely to hit.
Clash.
So we had to make sure that we absolutely had that perfect, because we knew it was going to come down to millimetres possibly. And in the end it did.
Yeah, and I think the bit which really showed off the use of the mesh fit was the outer rail. So the bridge obviously sits on the pintle and a roller track around the outside.
Yep. Oh, and yes, yeah.
That is a very short distance away from the pintle. So any deviation that we simulate there is going to have a huge effect at the nose of the bridge.
Yeah.
So I think we used the mesh fit on top of that rail surface just to completely follow the curvature.
Just to get absolute
really
accurate of it. And if you remember, we were a little concerned about the concentricity of the rail as well.
Yeah.
And when we ended up looking at it, when it got to the end of the travel, we were pretty close to falling off.
It was close.
Yeah, it was still on, but it wasn't a million miles away.
Well, that's the beauty of simulating this all from the beginning. We can give all this information to the client.
Yeah.
But yeah, so we've built up a history tree of modelling tools. So all these features, the sketches, the extrudes, the lobs, the sweeps, all the rest of it, as well as the more sort of design eccentric modelling where you've got the exact surfacing and the mesh fits, which aren't typical CAD tools.
Yep.
That's all in our history tree, which we can now...
We can still go back and edit those as we need.
Yeah.
They are still parametric features in that they're history based.
Of course.
But they are more organic shapes.
And now we can transfer this through into SolidWorks.
Yes, so I mean we do have the ability to transfer that history tree over to SolidWorks.
Yeah.
This instance we didn't use that because we didn't require that history. So we did end up just exporting it as Parasolid, but we could have done Step and IGS or any manner of formats, but in this case we used Parasolid because we didn't need to do any further modelling at this point. All we needed to do is create an assembly so that we could do a motion study on it.
Sure. And that was definitely in your wheelhouse. SolidWorks and all the rest of it's kind of where I step back, and that's your baby. Yeah,
it's my background. It's kind of what I learned modelling with. So yeah, we brought it into there. We constrained all the parts together. Specifically the pintle, the reference geometry for the pintle, the rollers on the rails. And then we could, once we'd set all those constraints, then we could set a range of motion that we wanted the bridge to travel through, and then conduct a motion study.
Yep.
And within that motion study, we could ask it to watch out for any clashes. And so as it goes through, it creates a video, but it also creates an output of where our clashes will be. And as it turned out, we did end up with several clashes. We had the blocks at the end of the bridge that it sits on were clashing with this area here. So when it got to its final seating place, it was going to clash.
Sure.
And I can't remember where the other ones
Yeah.
were.
I think we had some concrete round back in this area, maybe some of the blocks down here.
Yeah, I think
was it here as well?
I really can't remember. Maybe we should have looked.
Maybe, but we then presented this with the client. We showed them, if it's going to clash, how
it's going to be here.
How significant is that clash going to be?
And it was sub 2 mil the clash.
Well, I spoke to the client and they told me that they were able to go on site essentially with an angle grinder and just trim off the material. And they swung it very, very slowly because if it did get stuck, they want to be able to back it off. But they sort of were sat there watching these clash points and they agreed it got incredibly close. But
even with the
adjustments. Yeah, exactly. But no, as far as I'm aware now, the bridge is now up and operational.
Serviceable.
Yeah, exactly. So the client's happy. They've got a bridge that works, traffic's now able to go back and forth across, and there is no risk that it's going to get stuck to water traffic. So it's been a result.
Absolutely. Cool.
So regarding the I-beams, for example, we could see that they are a very mechanical design, but of course in the real world they're now not straight, they're swept, twisted, bent all over the place. So I think it would be useful to kind of describe what a typical workflow would be in Design X to achieve that end result. Yep,
fair enough. So what won't really change is a cross section of the I-beam. So what we're going to do is we are going to set up a plane, and there's many different ways we can set up a plane.
Sure.
On the data itself, so we can set it up from the data, we can set it up relative to some other geometry, whatever we want to do. But then once we've got that plane, we can then take a cross section through the data, and that cross section doesn't have to be where the plane is. It can be offset distance, so maybe I want it to start there, but maybe I want to take my actual cross section 100 millimeters further away, because that's where I've got better data.
Sure.
But equally, I can also do it rotationally, so I can do a rotational offset to get that cross section.
Or multiple sections.
Or multiple sections, and then it'll project it back. And then I'll get some what we call polylines, so it's lovely outlines which I can not snap to. Yes, they snap, but it's not a permanent constraint, so it allows me to manipulate it really easily and fluidly.
Like sketching on tracing paper.
Exactly, yeah. So it enables me to be really, really tight with what the mesh is saying, getting gaps and sketch entities. And then from that sketch, I'll then do another sketch of a guide curve to help me with the bow of the beam, for example. And then I will sweep along that guide curve the profile that I've drawn. And the other beauty about a mesh sketch is because I have those polylines, at any point, especially when you're chasing super high tolerances, it's all very well and good relying on your eyes, but within Design X we have the deviation analysis tool, and within a sketch I can check how far away my entities are with a whisker plot away from the polylines and get a really good information straight back. I can then sweep this profile out along and then go into 3D, so I've now got a CAD swept I-beam, and then I can hit deviation analysis again, and then it will colorise the CAD data, creating some contoured colours, which will reflect the deviation between the CAD and the mesh.
Yeah, which of course is key in this instance because accuracy is everything for this project.
Yeah, it is.
So things like the rail, the roller track, we can look at that and say our CAD data is within 0.5 millimetre of the scan data, and that kind of thing.
Yes, Well, I mean, although at the key points in this project we were chasing much higher tolerances than that.
Yeah, absolutely. So we're obviously a partner to Octon, and we use Design X all the time, both from a service point of view and obviously presenting it to potential clients. And I always ask the question, why can't I just take that scan data and put it straight into SolidWorks and use it directly?
It's about capability.
Okay.
We're dealing with a huge thing, a lot of points, and SolidWorks just can't handle that size of scan data at all. It does have the ability to deal with STLs, for example, and you can bring in point clouds, but it can't handle large data sets at all, whereas Design X can wonderfully handle huge data sets. So that's just from purely pragmatic, like, can it be done? No, it can't at this scale in SolidWorks. Secondary, or not even secondary, the Design X has the ability that we talked about of doing these mesh sketches, having the deviation analysis, generating CAD data, CAD surfaces directly from the mesh. Just the multitude of ways that Design X can interact with scan data natively, SolidWorks just doesn't have. I mean, could you do something in SolidWorks? If you made the data a lot lighter weight before it went anywhere near it, then conceivably you could do something. Would you want to bank the potential of blocking a
of course
a wall? No.
I think for me, I tell people you know, SolidWorks is a fantastic CAD application.
Yeah.
There's no doubt about it. But the ability to work with scanned data has always been a bit of an afterthought. Whereas Design X is very much
so.
Absolutely designed for handling scanned data of any quantity, but also has this fantastic CAD application built around it.
Yes.
And I think that's probably the best way that I like to put it to people in terms of explaining it. If there was one feature in Design X at the end of this project which really helped, what would it be? Would it be sort of the ability to do these mesh sketches, the flexibility in modelling, or maybe the deviation analysis tool?
I mean, the deviation analysis tool is kind of the be-all and end-all, but probably the biggest saver is the mesh sketch. Because to capture those organic surfaces
in the first place,
it would be ridiculously time-consuming without that functionality.
Yep.
So that's probably the biggest time saver, I would say.